Okay, here we go. So we're at lecture 5 already. So last week we covered correlation, regression, and logistic regression. And today we'll cover moderation effects. So it's back to ANOVA, so 2x2 ANOVAs and other designs. And I'll talk to you a little bit also about repeat measures ANOVA. So the goal of today is to get you more up to speed with ANOVA. We'll rehearse some of the assumptions about ANOVA, and you get to do some nice two-way ANOVAs and learn how to plot them, and talk a little bit about interaction effect. Well, nice. We'll see about that. So after today, you're able to actually complete the entire first assignment or the first exercise because everything is there. So there are easy marks to gain. So I would suggest that if you get stuck, don't fret on it. Just move on to the next chunk. Because you'll see there's like 40 or 50 different items, each worth 2 points. So if you get stuck on one particular thing, don't spend too much time thinking about it. They come also in chunks, so there will be a bit about ANOVA, a bit about regression, a bit about correlation. So if you can't figure out a bit about logistic regression, which is quite hard, for example, then do a bit about correlation or do a bit about plotting, which you are able to do. So it's your goal should be to do everything, obviously, but in the interest of time, focus on the things which you can complete rather than fretting a lot over a single small piece that you can't complete. So I recommend again that you work through the exercises. So next week, as you know, there's Academic Development Week, although we don't really call it that. But next week there is no taught session. I'll give you some things to work on, or some things. I'll post some things in your Blackboard folder. It's a time to catch up for the exercise if you haven't done any, or if you're falling behind, because some of you have fallen a little bit behind. And then if you have any questions, you can post them on the discussion board also about the assignment. And I recommend that you work through all the exercises first before attempting the assignments, because there's a very good correspondence between what you practice in the exercises and what I actually ask you to do in the assignment. So some of the things I'm going to say, have you tried the assignment? Have you tried the exercise before answering your question on the assignment, because you need to work through some of these things before posting questions. So before we move on, initially, so this is all about ANOVA. ANOVA has a very long history. It's the basic of experimental design. And initially, ANOVA was envisaged to have balanced design, so equal number of n in each group. So an equal n for each factor. But if that doesn't happen, then we have unbalanced samples. And that's where these things which I've talked to you about a little bit about, like sums of squares comes about, and like the calculation of different sums of squares. And that's what we'll be focused on here. This is not very visible here, but it will be visible on your slides. So if everything is uncorrelated, so if all of your factors are uncorrelated, none of this matters at all. So if all of your factors are completely experimentally separated, or there's no correlation between this, the sums of squares really doesn't matter, because you have this type of scenario: the sums of squares for A, sums of squares for B, and the sums of squares for AB, for example, for the interaction. So, however, if the predictors correlate, then there are several options in which you could evaluate those effects of AB and of the interaction AB, and they're visualized in these Venn diagrams. So you could, for example, just look at this type of effect, like the true effect of SSA, but without looking at U, V, W, because they overlap with the interaction or they overlap with B. So you could, depending on that, you would partial out some of these effects. And that depends on your statistical assumptions you have. So the terminology is you have type 1 sums of squares, and they're known as sequential sums of squares. And this is the default for R, and it's basically the order in which you put in things influences things. So we put in A first, and that is T plus U plus V plus W, and then you put in B, which is X and Y, and then you put the interaction, which is Z. Yeah. So that's the sequential way of doing it. So first we care about this most, and then we see what happens if we put in this, and then we see what happens if we put that tiny chunk of Z in. Yeah. There's hierarchical. So this is the putting in T plus W. So T plus W, and then X plus Y. These two, and then as a final thing, putting in Z. Yeah. So it adjusts for the terms for all other terms except the higher order terms, including the same predictors. So again, it usually helps to draw out all these Venn diagrams to see what happens when you do different sums of squares. Yeah. And the most commonly used one, because it's the most conservative one, and it's also the one which is the default in SPSS, and most likely you'll encounter this. But sometimes, based on theory, this might be more sensible because you have a stronger hypothesis about A than you do about B and its interaction. So it might make more sense that you first look at for the effect for A, and only then start looking for B, and only then start looking for the interaction. Yeah. So even though this is the default for most software packages, sometimes you should take a step back and think as to what is it that I'm trying to achieve. Do I have a stronger hypothesis about A than I do about B and its interaction? Then perhaps this one might be a better solution than the ones you than the default. Yeah. So type 3 is known as marginal sums of squares or orthogonal sums of squares. They first test T, then X, and then Z. So it doesn't take into account the Venn overlap diagrams. Yeah. Okay, so it's the assesses. So this assesses the contribution of each predictor above and beyond the other one. Yeah, because it's not looking at the overlapping things in the Venn diagram. Yeah. Again, if you have this type of situation where everything's uncorrelated, none of this will matter because you don't have this UVW type of situation. Yeah. Does this ring any bells? Is this anything you've come across, like sums of squares in your undergraduate, or no? Okay, this is just taking a step back. This is how ANOVA was originally originated. I think it's good to know because in psychology we're mostly doing this, but you might come across some other fields where they use type 1 or type 2. And again, I have to tell you about this because the default, if you don't do anything, will be type 1 in R. Okay, so which one to use? Pick the one corresponding to your hypothesis. So if you have strong theoretical predictions for A, and you want to control for things, then perhaps type 1 is your best option. Yeah, so if you have much better theory about A than you do about B and its interaction, then perhaps you should do type 1. But most of the time, your choice will be between 2 and 3. So that's what most of the time you would think of. Like for the highest order interaction, all of them will give the same statistical answer. But the type 2 is most powerful when no interaction is present, and the type 3 is the most conservative with regards to assessing the main effects. Yeah, and that's because you remember the type 3 only takes into account T, X, Z, and doesn't take into account the overlapping things in those Venn diagrams. So that's why it's the most conservative. And that's also why for most software packages, this will be the default, and that's also why psychologists might tend to like that. Yeah. But in some cases, you might be better off picking type 1, type 2, depending again on your hypotheses and depending about your assumptions. Yeah. So if you don't have a very good intuition about the interaction effect, but you do care a lot about the main effect, then perhaps type 2 is the one you want to look at. Yeah. So because all of these balance the power you have to detect these interaction effects versus the main effects. Yes? Does that sort of seem sensible, make sense? Okay, so I've said a lot about these interaction effects, but I haven't really defined it. So can anybody of you explain sort of what the interaction effect is and why we care about them, particularly in psychology? No? So what is an interaction effect? Have any of you tested an interaction effect in your thesis or come across this type of thing? No? So I've been just talking in a vacuum about interaction effects for the past 5 to 10 minutes. But so the interaction effect is, you can think of it as a multiplicative effect, and it's basically we care about it in psychology because it's about the interaction, usually about the environment and a personal trait, for example. So we think that people high in conscientiousness will behave differently in a high work stress setting compared to a low work stress setting. Yeah, so you have hypotheses about something interacting with something else, and most of the time it's between an individual trait and an environmental trait. Especially in social psychology, nearly everything is by these 2x2 interactions because you don't predict that everybody will respond in the same way to your experimental manipulation, but you predict that some individuals scoring very high or very low on a trait will show a stronger response in terms of your manipulation. Yeah.
How would that differ from the main effect?
So because here we're looking at whether the effect is stronger, so we don't predict everybody will respond in the same way. In this work stress situation, we predict, for example, that especially people who are highly conscientious will be more likely to burn out because they're more concerned of some sort. So depending on your dependent variable, so you're predicting that your manipulation or your effect is not the same strength across a different variable. And so in statistical terms, that's basically a multiplication. So it's multiplying two factors or two effects. So there could be other examples from health psychology or from other things, but most of the time we don't predict that everybody responds in the same way to, for example, to a stimulus. So we will look at interaction effects because we predict, especially people who are scoring high in a personality trait or low in a personality trait, for example, will be more responsive to taking a certain type of drug or taking having an effect of that type of drug. So, for example, you could think again of a medical situation. So, if you, for example, give antidepressants, you might predict that not everybody responds in the same way, but some people will be more susceptible, perhaps men or perhaps women. And you might predict that these effects will be stronger or less strong depending on a second or third variable. Yeah? Does that sound sensible? So most of the time we have some hypothesis about main effects, but usually we predict also there's some variation in how strong the effect is depending on another variable. So moderation is synonymous with interaction. So if you look at moderator analysis or interaction analysis, they're the same things. Moderation is not the same as mediation. So mediation means that, we'll come to that in a bit. Mediation means that something acts in the middle as a causal mechanism for something else. So something can be a moderator but not a mediator, for example. Yeah, so you will have to do some thinking as to whether your variable is a moderator or a mediator. But when we're talking about causal mechanisms, for example, we think that there's a gender difference in risk-taking because there's a difference in personality between men and women, then that personality measure is a mediator and not a moderator. It's a causal mechanism which tries to explain the gender difference that we observe in risk-taking. Okay? So when you think of causal mechanisms, we're looking at mediators. If you think about the effect being adjusted based on high and low of a certain trait or being different between genders or age groups, then we're talking about interactions. And it's nothing more, nothing less than multiplying terms in an interaction or in a regression. Again, regression and ANOVA are very much alike, so it's the same type of principle. Okay, so how you go about in doing this? So you check the relevant assumptions first. Because it's ANOVA, do you recall what the assumptions are you have to test? Anybody? Not Ben? Linearity was one of them, and what was the other one? Yeah, homogeneity of variance, and yeah. And so you remember how you tested the homogeneity of variance? What you did to do that? Hello. I was still asking you. So, do you remember how you tested the homogeneity of variance assumption? How we did that? What? Okay, so don't worry, but we offered two options. So one was the Bartlett's test, and the other one was the Levine's test. So you remember that one was more responsive depending on linearity of your variables, and so Levine's test and Bartlett's test, and you remember probably that we checked linearity of some assumptions by these visual checks. Yeah. So if you don't remember, go back to the slides of week 3, but that's where we covered these assumptions and how we check them. So often you will see these type of plots. Yeah, so this is sort of an interaction plot. So you predict, for example, that depending on low and high training and low and high autonomy, the job performance will differ. So especially if you have high training and high autonomy, then you'll have high job performance. Yeah. So in many different cases in occupational psychology, in social psychology and clinical psychology, you'll find these type of plots, and they're interactive plots. It's showing how the effect of a manipulation or of something else differs depending on another trait. So in this case, you can administer lots of training or no training, and you can see if people are in an autonomous or non-autonomous job, and then you can see how the effect changes as a function of job performance. Yeah, and so there's lots of hypothetical situations you could draw out like this. But this is really the bread and butter of what psychology does, because again, we usually care about individual differences. We don't predict everybody responds in the same way to a certain type of situation or certain type of trait. And so that's why we care about these interaction effects. Is that becoming more obvious now, why we should care about interaction effects and why it's important? So have you come across an interaction design in your bachelor thesis or perhaps your internship now? And if so, what shape was it? Because this was one shape. You come across something like this, or you're all doing qualitative methods and it doesn't apply, or have any of you come across this type of no? let's see if I can, I don't think they put a pen here, but we had this type of thing. So you could predict that one thing goes up and the other one goes up less steep. So that's sort of similar to this type of situation. They both go up, but one goes up much steeper. You could have a line which is flat, so there's no response in one group and one going up quite strongly. The strongest interactions are these type of crossover interactions where one group goes down and the other one goes up. Yeah. But if we have a situation where we have two parallel lines, then we have no interaction, right? Because it's not changing based on this third variable. It's just a shift in the other dimension. Yeah. Because there is no change then based on this. So if we had two parallel lines like this, then that wouldn't constitute an interaction. The most powerful interactions are where one group goes down and the other one goes up. Yeah. And if you haven't come across them, they're quite popular. So you will come across some of them probably when you read about your work or when you read about for your internship or for your master thesis, because they're quite common. So what other forms can interactions take? So we have looked at very basic interactions. So these are just two variables. We have three variables. In principle, you could have 4 or 5 variables, like 4 or 5 interactions. They become increasingly less plausible as you add more and more variables to it. But you can, for example, again, this is not usually this is not visible, but here, for example, let's see, this is the level of college education and like whether you care about climate change. You can see in this group, for example, if they're high school or less, there isn't much variation. But as it goes up, like if they are liberal versus conservative, yeah, like extremely conservative or extremely liberal, they care about their environment more or less. So this is a true interaction because we have educational level, we have ideology split into extremely liberal, extremely conservative, and somewhere in the middle. And then we have the effect of ideology. Okay, so we're going to do something like that, but again with a different data set. We're going to look at tooth growth in guinea pigs, and that's because it's a standard data set, and because also quite broadly, I want you to just not work with psychological data in itself, but also quite broadly work with some other types of data sets like airlines or something, because some of you might become data scientists, which means you'll have Facebook data or data about guinea pigs or data about monkeys. And so what you have in this data set is the response is the length of odontoblasts, and these are cells which are responsible for growing teeth, and in 60 guinea pigs, and each animal received 1 of 3 doses levels of vitamin C. And so during a period like 0.5, 1, and 2 milligrams a day, and they could receive it either via orange juice or via ascorbic acid. So you have the dose, and you have the, so we can look at 2 factors here, like dose and levels of vitamin. And we want to do the first step, and so you're going to go back and load the data from ToothGrowth database, test the assumptions for a 2x3 ANOVA. So remember, that's a linearity check, and that's a check for the homogeneity variance. And you have to convert those to a factor because it will be listed as a number, so it's 0.5, 1, and 2, but we want to treat it as a categorical thing rather than a continuous thing. So what are the solutions in case of value violation? So you don't have to run them, but you should think back as to what it is that we can do in case we have violations of those assumptions. And then don't click just yet, but the solution to this type of thing, you can click on there. Yeah. So load the ToothGrowth database and check the assumptions from lecture 3 for what we did, which is the homogeneity variance check and linearity check. And come to think of it, it's like I didn't probably explain this very well, but this is probably a 2-way interaction, not a 3-way interaction, because you only have 2 variables and 1 dependent. So I messed up there. So